Hey. Okay, welcome everybody to the first of what's going to be quite a few talks over the next couple of weeks. I think we have four speakers for the Gemini North talk series in the next couple of weeks. So to kick that excitement off, today we have Raja Guhathakurta visiting from UC Santa Cruz, UCO Lick. Raja got his bachelor's at the University of Calcutta when I was just a little tyke way back in the day, and then went on to Princeton University to get his master's PhD, has been a Hubble Fellow, and is now professor at UC Santa Cruz. He was the department chair of the Department of Astronomy and Astrophysics there. I think just recently sunsetted for that. And so now he's free to travel the world and talk science and talk outreach and everything. I couldn't introduce Raja without talking about his outreach and his dedication to mentorship. He had the misfortune of mentoring me when I was an undergrad at UC Santa Cruz, and he made it through that admirably. But he has mentored tens of PhD students, scores of undergrads, high school students, and he works. He has a dedicated passion to doing outreach here on the islands and all over the world. And so today he's going to talk mostly science, but I think he's also going to talk about some of the outreach activities maybe towards the end of his talk. So with that, please, Raja.
Thanks. Thanks, Brian, and thanks, Emma. Thanks everyone for spending part of your Friday afternoon with me. Can people hear me okay on Zoom, and people hear me okay in the room? All right. So I'll talk about the resource stellar populations of the galaxy we live in, Milky Way, just a little bit about that, and then mostly focus on Andromeda and Triangulum. And I brought a couple of visitors with me, Sunny and Azrael. They're both from Molokai. I first met them at their school, the Akaula School in Molokai. And Azrael has been working with me on something that relates to what Deborah works on, which is comparing the performance of PyPit, data reduction software, on DEMO spectra with the performance of the older IDL-based Spec2D pipeline. So what I'll talk about is really the work of many people, not just Azrael, but many people, and I'll try to acknowledge them as I go along. Let's see. So this image of Andromeda is one that is taken by Robert Gendler, astrophotographer who moonlights as a doctor during the day. And but this picture that's just come into view is taken by Laurie Hatch, a very talented photographer who lived on Mount Hamilton Lick Observatory for many years, and she took this beautiful a photograph of the Mauna Kea sunset. And I'm showing this here because a lot of what I'll talk about is based on the Keck telescope, using it to study the resolved stellar populations of these three galaxies, the Milky Way, Andromeda, and Triangulum. So I did my own little bottom-up simulation of galaxy formation last night. That's what I'm showing you here. This is how the Milky Way formed, bottom-up. And I'll talk about three surveys, the Halo 7D survey, something it's quite new, BP3M is something that Kevin McKinnon, recently minted PhD from our group, is working on. This is looking at Bayesian techniques to look at parallax, proper motion, positions, parallax, proper motion. He's applied that to stars in the Milky Way halo. And I'll talk about something called NGVS, which is based not on Keck, but based on the Cairns-Francois White telescope on Mauna Kea. And these three surveys all target stars in the Milky Way halo. And I'll say a little bit about M31, M32, and M33. So through another sea of acronyms, SPLASH, TREX, FAT and FASTER, Hubble surveys, SPLASH and TREX are Keck DEMOS surveys, FAT, FAST, FATTER are HST surveys, and HST promo is HST proper motion using Hubble to measure proper motion. And then if I have time, I'll say a little bit about nearby galaxy groups. This is in the local volume, but outside the local group. And this is through the lens of a survey called Pisces. Okay, with that, I'm going to start again. I'm going to start with the Milky Way, then say a little bit about Andromeda and Triangulum and M32, and then finally talk about nearby groups. Okay. Accretion history of the Milky Way stellar halo is something we're interested in. There are a lot of people. There's been a huge revolution in our understanding of the Milky Way, especially because of Gaia, and before that with SDSS. There have been wonderful surveys of the Milky Way, and sort of riding the crest of that wave, we decided to do this survey where we look at the sparse Milky Way halo with Keck and Hubble, but you can't help but look through the Milky Way halo at the universe beyond. So it's looking at and through the Milky Way's remote stellar halo. This is a survey called Halo 7D. And let's see if the name appears here. I think it's at the, oh, I can see it there. I can't see it on my screen. Okay. So what we did was we used Hubble archival data. So from a couple of very large programs, most notably the CANDLE survey, which was a multi-cycle treasury program with Hubble. The CANDLE survey surveyed a few patches of sky to study distant galaxies. But of course, as you study these distant galaxies, you can't help but capture foreground stars in the Milky Way. So we have deep multi-epoch HST imaging, and the galaxies that were the targets of these surveys are really important for the study of foreground stars, because the galaxies form this cosmic wallpaper, similar to what you see on that image. They form this cosmic wallpaper, patterned wallpaper, against which you can measure the very slow crawl of Milky Way stars, to measure their proper motion. It's like trying to watch an insect crawl across a wall. If the wall is painted flat, like, with no ridges, it's very difficult to track the motion of that slowly crawling insect. But if there's finely patterned wallpaper, you have many points of reference against which to measure the motion of the object. And especially if you take into account camera distortion between images taken, decades apart, the patterning becomes important. That gives you the reference frame with which to map the distortion of one epoch to the camera distortion of the other epoch. So we've been using that, and we've measured the proper motion of about 1,000 main sequence stars in the distance range 10 to 30 kiloparsecs. So typical distance would be 20 to 25 kiloparsecs. These are main sequence turn-off stars in the sort of remote, I would say, halo. Remote in the sense that the typical distance is maybe 3 times the distance of the solar system from the center of the Milky Way, but they're out in the halo, not in the disk. Now, with this Hubble program that measures proper motions, we also have a Keck spectroscopy program to measure the third component of motion, the line of sight velocity. And we did some really deep integrations because the stars are faint and it's hard to measure meaningful spectra. So we have up to 32-hour integrations of some fields, but 8 was more typical. And we got line of sight velocities for about a quarter of the stars for which we have proper motions. Now, again, when we design a DMOS mask and put some slits on stars, we would be wasting slit mask real estate if we didn't put them on background galaxies. So we have exquisite spectra of about 1,500 galaxies in 4 of the CANDLE's fields, so Good South, Good North, EGS, and Cosmos. So this is what we're trying to measure is 7D. So that's 3 dimensions of position, 3 dimensions of velocity, and the 7th dimension is chemistry. The 7th dimension is more than one number, but it's the 7th dimension of information. And the names you see at the bottom are in 2 rows. The first row are people who are interested in the Milky Way halo side of things. The second row are people who are involved in the distant galaxy side of things. So it was really 2 completely different surveys sharing the same Hubble archive and sharing the same piece of aluminum, the same DMOS mask, some slits for one program, some slits for the other program. So we've had a few papers come out of this on both sides of the, or for both of these projects. So I'll show you a little bit. This is the PhD thesis of Emily Cunningham, and she worked closely with Alice Deason, who was a postdoc at Santa Cruz at the time. Emily's now a postdoc at Columbia University. So she's doing her second postdoc. She was at the Flatiron Institute before that. And Alice Deason went from her Hubble Fellowship at Santa Cruz to now being a faculty member at the University of Durham in the UK. Just to show one result from one of Emily's papers is these are 4 fields. You can see their names in the names of the fields are, the color coding shows you which field we're talking about. EGS, extended growth strip, GOODS North, GOODS South, and Cosmos. And what you're seeing in each case is the average rotation speed, so V5 in the upper top left panel. You're looking at the dispersion in the radial direction. I mean, this is what you can do if you have 3 dimensions of velocity, 3 dimensions of position. You can see that the distribution of distances, the main thing I want you to take away from this is something not a surprise at all, because if you poke 4 pencil beams through the Milky Way halo, you don't measure the same thing along the 4 lines of sight. You get the Milky Way is halo is still virializing. There's lots of recent cannibalism events that whose debris you can still see. So it's not a well-mixed halo. This last panel, lower right panel, is looking at the beta parameter and isotropy, amount of energy in the tangential direction in the numerator there, amount of energy in the radial direction, 1 minus that. So it's if you had perfectly isotropic orbits, you'd get 0 for the beta parameter, and if you had highly radial orbits and the very little tangential dispersion, beta would be 1, beta would be negative infinity if things were on purely tangential orbits. So one of the things that we can do with these data is using the spectra. One can look at metallicity and alpha, light element to ion ratio. And this was a paper led by Kevin McKinnon. He just finished his PhD in 2023. And if you look at the line of sight averages of the metallicities and alphas, again, you can see that chemically too, the galaxy is not well mixed. And there are correlations between the chemical properties and the orbital properties. So this is again the work of, I should remove the word student from it because it's UCSC PhD 2023 now. And Kevin is going on to do a postdoc at CETA with Judah Kohlmeyer. And this slide is really a slide that's trying to interpret the measurements of an isotropy in the galaxy. This particular, this is complicated, so let me take a moment to explain what this is showing. These are 2 simulated galactic halos from Bullock Johnston 2005. In the upper halo, things are relatively well mixed, and you can see that. So there's no data here. These are pure simulations of galaxy formation. Let me start with the leftmost panel. What that's showing, every dot represents an accretion event. The size of the dot represents the mass of the thing that got accreted. And the vertical axis tells you when things got accreted, time since the accretion. So when things are high up on that plane, it's an early accretion event. When things are low down in that diagram, it's a recent accretion thing. And the main difference you see between these 2 galaxies is this has some late accretion. The lower simulation has some late accretion, and whereas the upper one doesn't. And those are the 4 lines of sight that you see there, the 4 lines that you see rotating around the simulated halo. You can see them in the ATOF projection as well as points there. In the ATOF projection, the simulations are being rotated with the 4 lines of sight being fixed. And the main thing to see is in something like VGSR, the typical velocity, distribution of velocities, there's very little variation across the four fields in the well-mixed halo. Even with four fields with limited numbers of stars, these cumulative distributions are very close together for the upper simulated halo. They're much more spread out for the lower simulated halo. In other words, even with as few as 4 lines of sight, you can distinguish between accretion histories. You can tell whether there's been, our galaxy doesn't look like the upper simulation. There's clearly been recent accretion. So we've done this. Miranda's Apfel is the lead author of this. She's done this for all 11 Bullock-Johnston halos. She's done this for a future survey that we've started to do that involves 30 lines of sight, not 4. And the goal is to use these simulations, compare them to the data to learn something about the accretion history of the Milky Way. Okay. I want to change gears a little bit and go a little bit.
Sorry, can I say a quick question about that? Are there degeneracies that exist in terms of the kinematics of the accreted galaxies and the mass distribution of the particles that are accreted? I would imagine that there might be.
Yeah, so what matters also is the x-axis of that diagram, which is the circularity of the orbit. So if you have a highly radial orbit, you're going to create one kind of signature. If you have highly radial orbit, you tend to create shells. Whereas if you have more tangential orbits, you tend to create streams. So depending on what you're measuring with your data and what radius you're sensitive to, there is certainly more power. This is just one parameter being shown here. We have 7 different parameters that one can look at. And this is exactly the kinds of things that are being combined into this paper that Miranda is looking at. Again, it's based on not Halo 70, but a notional future Halo 70 with 30 lines of sight. I don't know if that answers your.
Yeah. So you're able to break those degeneracies with all the parameters at your disposal.
Yeah, to some extent. Now this is what I know, I mentioned remote halo, but by all accounts, this is like the inner halo within 50 kiloparsecs of the center of the Milky Way. I would consider that the inner halo. I'm going to say a little bit about the outer halo next. And this is really trying to measure the extent of kinematics of the part of the halo that's beyond 50 or beyond even 100 kiloparsecs. And for this, we're using distant RLRA from the next generation Virgo cluster survey. I'll compare our results to results from other time domain surveys. Now, the next generation NGVS stands for the next generation Virgo cluster survey. In imaging the Virgo cluster, in imaging 104 square degrees of the Virgo cluster using the Cairns-Franz Hawaii telescope and MegaCam, 104 square degrees in 4 filters, UGIZ, you can't help but make measurements of stars that are in the foreground of the Virgo cluster. The Virgo cluster is at 16.5 megaparsecs on average. That's the typical distance of a galaxy. But you have RLRA stars for which you can measure you can detect them, and you can measure their properties, including their distance, and that's what I'm going to talk about. I do want to say a little bit about NGVS. It was designed to be a survey of galaxies in the Virgo cluster, and the people who set up this survey knew that they were interested in large angular scale, low surface brightness features. This is intra-cluster light from destroyed galaxies, cannibalized galaxies. They were interested in low surface brightness in the Virgo cluster. And we know that low surface brightness and large angular scales is a difficult measurement to make, in particular because the Earth's atmosphere can have variations across a degree or two. The atmospheric air glow keeps changing and can have large angular scale variations. In order to average over this, they decided that we shouldn't just take a one of these 104 square degree patches, there's 104 pointings of CFHD megacam. So we don't want to just pound on one field, complete it, and then go on to the next field. Instead, we want to build in a time gap so that we give the atmosphere time to change, and we can effectively average over variations caused by the atmospheric air glow. So for this reason, even though they might have been doing 6 or 8, 10-minute exposures in the U band, the typical separation between exposures in a given field is an hour. You take a 10-minute exposure, then go off an image 4 or 5 other fields before coming back to that field. And the idea is to let the atmosphere do its temporal variation so that you don't mistake air glow variations with something astrophysical.
This is with like low surface brightness objects in the Virgo cluster.
That's the scientific interest was that, and the
Yeah,
thing they were
that's
trying to
the
guard
technique.
against was air glow variations. Now this made this a very effective time domain survey for variable stars. RLRE have periods of several hours, so this building in of these gaps, even though it wasn't designed as a time domain survey in the traditional sense of the word, we decided to mine the data, and we found about 200 RLRE, including about 80 that had already been detected by the Pan-STARRS 1 survey. These 80 were at the bright end of what we found. So this is what I'll talk about. We found, bottom line, we found a couple of RLRE whose distances are beyond 250 kiloparsecs, 300 kpc. These are the most robust to date detections of RLRE, and I say most robust, I'll get to that in a second. There are at least 2 other competing surveys. There's a survey done with this dark energy survey, DES, has found RLRE, much bigger area of the sky. They found many, many more RLRE than we have. But our single epoch precision is significantly better than DES. And a third survey is something called HITS, which is a high cadence transient survey. They worked in a single filter, but again, their aerial coverage was more than ours. But it's really the single epoch precision, number of epochs that matters, and what filters you use could matter as well. So here's some examples. We have about 30 measurements. These are folded light curves. You can see an RRAB example in the upper left, and an RRC, more sinusoidal variations, in the lower right. RRCs tend to have a lower amplitude, but we have about 30 measurements across 4 filters. And it's really the excellent photometric precision that is the key here. I'll explain what I mean by that. So this is a recovery of periods of the 80 or so RLRE that were in this 104 square degrees that were discovered by Pani Cesar and company using Pan-STARRS. Most of them lie like pearls on the one-to-one line, but a few are on the beat frequency alias lines. Because our measurements, PS1 measurements, have a natural cadence of 24 hours, or one every 24 hours. So if you take the actual frequency of the RLRE, and the frequency of one per day, 1 plus F and 1 minus F will give you, you get aliases, and so a few of them land on those lines. We think we got the period correct because we have better precision and better samplings, actually somewhat better cadence, but and then there's some where they're so bright that they're saturated in our database and we don't recover those. This graph is, what this is showing is, when you point your telescope at a patch of sky and you look at the point sources, most of them are not variable. Most of them are stars that don't have any variation. So if you look at the empirical RMS, empirical brightness variation in magnitudes on the y-axis as a function of G-band magnitude, you get a graph that looks like that. So the dashed line is the sort of the ridge line based on the median photometric error as a function of G-band magnitude. And the comparable curve for DES looks like that. and for hits, it looks like that. Okay, so this, and again, these are empirical data. What you do is, so I'm showing you the best fit lines for DES and hits. I'm not showing you that data, but what in all cases, you take the majority of the objects in the survey, which are non-variable. You look at their empirically, you look at their measured brightnesses across the different epochs, and that's what's being plotted here in the G-band. And it's the fact that our single epoch precision is better that helps us. The depth, if you look at 0.05 magnitudes, the depth, we go about 1.7 magnitudes deeper than DES and a little more than 2 magnitudes deeper than hits. This is a paper that Yuting Feng, PhD student at Santa Cruz, is working on. This is sort of the pizza chart version of this, pizza pie version of this. And like I said, there's one star beyond 300 kpc, but there's a handful beyond 250. It's starting to get where we're not looking in the direction of Andromeda. We're looking towards the galactic pole, the Virgo cluster, sort of towards the North Galactic pole. But this is 30% of the distance to Andromeda, 40% of the distance to Andromeda. Andromeda's halo appears to be comparably big. So, gone is the idea of Kant's idea of island universes. Galaxies aren't islands at all. Their outer parts are overlapping. This big cluster you see over here, this is the Sagittarius string that you're picking out, but it's very close in compared to the stars we're interested in.
M31 is more massive than the Milky Way, right? So how do you know,
probably has a bigger halo. Yeah, probably has a bigger halo.
How do you know which galaxy
this one belongs to? So we're not looking in the direction of Andromeda. This is towards the North Galactic pole.
Yeah.
But also, we're starting to measure velocities. And these velocities we've found so far, the spectroscopy we're doing has been with ESI on Keck. And the velocities we are finding so far seem to be centered on 0. We've followed up some of the DES RLRE, some of the PS1 RLRE, some HITS RLRE, and our own. The other thing spectroscopy lets us do is occasionally distant quasars will get misclassified as RLRE. We're finding them and weeding them out. We haven't found any in our survey so far. We found a few in other surveys. And again, cadence, how many measurements you have, what filters you have, and having multiple filters and watching things go down altogether, the sure sign is something that has long period variation and is likely to be an AGN or a quasar. So I don't have the time to show you examples of those, but once you get a spectrum, it's very clear when something is not an RLR. These are density profiles based on our data. The data points are based on NGVS. That bump you see around 40 kpc, that's the Sagittarius stream. We've made no attempt to remove them. But the other surveys, DES and HITS, I'm showing you their fits as they performed it out to the radius to which they believe their data. So DES did a fit out to 100 kpc, HITS went out to beyond 200. We're doing our fit out to 300. We've done completeness tests, and our completeness doesn't fall off until a little beyond that. We're about to do contamination tests, which are a lot harder. That is injecting known quasars into our survey and seeing how the algorithm does. That's something we're in the process of doing. I won't talk about this, but this is Yuting's PhD thesis, part of this, including the spectroscopic follow-up. All right. How am I doing on time?
20 minutes.
Okay. 20 minutes to go.
20 minutes.
Okay, perfect. And then we'll do questions at the end.
Yep.
Okay. All right. Let's say a little bit about Andromeda's teledynamics next. I love showing this video. If you've seen it before, I'm sorry that I'm inflicting this on you again. But this is the arc of the Milky Way. And in the foreground, in the background of the Milky Way, that little ellipse, I'm going to point to it on my screen here so that people in Zoom know which one I'm talking about. That's Andromeda, a distance of 0.8 megaparsecs, 2.5 million light years. And let's see if this works. So this is it's a zoom in that was prepared by a team at Space Telescope, Joel Clavet and collaborators. And as we zoom in, you'll see the Andromeda satellites, NGC 205 and M32 just went by there. And but we're going to zoom in until you can see the full details. Well, not the full details, but you can see sufficient details in the Hubble image. of this part of Andromeda's disk, you can see that it's made up of stars. It's made up of stars of different colors and temperatures. And but you can see dust patches. You can really see those dust patches going through. The stars look red in those patches because we're seeing through a layer of dust in Andromeda's disk. We've used this database to target stars for spectroscopy. And the great thing is once you have a Hubble image, you can tell when a star is going to be contaminated at ground-based resolution or not. And that's how we select stars for spectroscopy. This is, we've been using this to study the similar data in M33. And we've been doing spectroscopic campaigns on N31 and N33's disks. The results tell the populations in the disks. This is, I'm showing you an old result from 2015 from Claire Dorman's PhD thesis. By the way, I just realized that my join audio thing is something that I haven't clicked. Do I need to do anything?
No, it's okay.
It's okay?
Exactly what you want to do.
I don't want to do that.
Yeah, don't do anything with that.
Okay,
You're good.
good to know. Keep my paws off that. Okay. I wanted to show this panel here because in a single image, it tells what I consider to be an interesting story. So every dot you see in the 3 panels, the 4th panel, the lower right panel is a Herschel image of Andromeda, but to the same scale as the other 3 panels. So you're looking at a sky map of stars in a section of the disk of Andromeda. You can see that the dots in the other 3 panels don't trace out the full ellipse because we've only mapped out about a third of Andromeda's bright disk. Now, every dot is a star for which we have a spectrum. The X marks the center of the Andromeda galaxy. So you can see we have a lopsided survey. We're now imaging the southwestern side. So the survey is gradually becoming more symmetric. But the color, the 3 panels are stars of different ages. You have young stars, massive stars in the top left. You have intermediate age, intermediate mass stars in the top right. And in the bottom left, you have long-lived stars, low mass, old RGB stars. So the parts of the CMD we use to do this demarcation, if we look at the upper main sequence, so young, bright blue main sequence stars, luminous blue main sequence stars, we look at super TRGB, AGB stars, carbon stars, and the like, and oxygen-rich intermediate age stars, that's the AGB. And then RGB are stars that are below the tip of the old RGB. So these are stars that live for several billion years. The color coding of each dot is important. For every dot, we look at we draw a circle around the star, and we look at other stars of its type. So if I'm doing this around a main sequence stars, I look for other main sequence stars around it, and I ask, what is the dispersion of velocities? So if you see a dark color, that means it has a low dispersion. That's the color bar at the top. If you see a light color, if you see an orange or a brown, that means there's a high dispersion of velocities of that kind of star in a circle. This is measuring the degree of order versus disorder in the galactic disk as a function of stellar age. And you can see a very clear brightening of the color from the younger stars through the intermediate age stars to the old stars. This is how the demarcation is done into different age groups, because the left CMD is the entire CMD from Hubble, and the inset are the bright stars that are bright enough for us to get spectrum. And red are RGB stars. You can there are some stars that, some regions of the CMD that we're not using because there we have mixed populations, in fact, including foreground stars, we're excluding those. But this is our rough demarcation of young, intermediate age, and old. In fact, we've divided the intermediate age into luminous and not so luminous AGB stars. And here's the difference. The blue histogram represent young stars. They have a dispersions of order 30 kilometers per second, but the RGB stars more like 100. This is line of sight, local dispersion. Another way of looking at this is dispersion as a function of age. The filled circles are from Andromeda if one assumes a constant star formation rate. But if you assume a declining star formation rate, then of course the mean age of the RGB goes up. And so the points, the older points move to the right. Very different from what is seen in the Milky Way disk. That's what's shown in orange and pink. It's a little bit of apples and oranges in the Milky Way. It's a solar neighborhood sample, internal view of the Milky Way, whereas Andromeda, it's an external view, somewhat more global measurement. This is Claire's PhD thesis from 2015. Another student, Amanda Quirk, looked at color coding stars differently, not by dispersion, but by their velocity alone. And so in the top, you can see that every dot, the color of each dot is the velocity of the star. In the lower panel, the color of each dot is the mean velocity of the neighbors, not the velocity of the star itself, but the mean velocity of the neighbors. So it sort of averages out the dispersion. And what you can see for young stars is there's a very clear gradient in velocity because you're looking at a rotating disk, but that gradient is less steep in RGB stars. The color variation is from purple to red rather than purple to yellow. This is saying that there is significant asymmetric drift for the long-lived stars. Not only have they been kicked around to have high dispersion, their net rotation has gone down. So sigma has gone up and V rot, the average V rot has gone down. So this is asymmetric drift now as a function of stellar age. So something is dynamically heating the disk of Andromeda, and that something seems to not be a single event because we seem to see a trend with age. Doesn't seem to be a step function. Again, this is now looking at asymmetric drift as a function. Every star's neighbors, we can get one data point on the asymmetric drift plot, and RGB stars generally have significant asymmetric drift, whereas the asymmetric drift is closer to zero for young populations. Again, this is Amanda Quirk's PhD from 2022. She's a postdoc at Columbia University now.
That's just a small patch of Andromeda?
That's looking at about a third of Andromeda's disk. Now we've imaged and done spectroscopy for another third of the disk. So our current coverage is about 2/3 of the bright disk. The sample I showed was about 1/3.
So the heating is everywhere, probably.
Yes. No, you're asking a very good question. We see evidence that at the end of the bar, there's extra dispersion there. But it's not like it's zero everywhere else and just high at the end of the bar. But we can see an elevation near the end of the bar. And so the things that could be stirring up the disk are, of course, a bar. When I was in grad school, molecular clouds were very good at dynamically heating the disk. They seem to have stopped doing that these days, but satellite bombardment can do that too, of course. But yeah, so we're trying to, I think the next step is to try and figure out what, are there multiple things that are heating the disk? And we've done this, I don't know, I'm going to jump through this, I'm not going to, but we've done this for, so this is the part of the Andromeda's disk that we're now covering. What I showed you was the upper left. We're now covering the lower right, the southwestern disk. We've also covered M33. I'm going to skip through this. Too many slides. Sorry.
Roger, I think we have a question online from Avi.
Sure. Avi.
Yeah. So are you seeing is this analogous to the thin disk, thick disk structure that we see in our own galaxy? Where there's heating, and the thick disk has slower rotation than the thin disk.
Very analogous to that, very analogous, except if we look at RGB stars, we don't see a thin disk at all. I think that's the difference. We see a thin disk in young stars and intermediate age stars. We don't see one. Now, mind you, we're using kinematics as a proxy for thin versus thick, of course. But modulo that, we don't see the dispersion. It doesn't seem like there's a cold and a hot component in the RGB stars. It seems to be all.
Distribution is different.
Yeah, the distribution is different. Qualitatively similar to the Milky Way, but in this detail, different.
Thanks.
Sure. So I'm skipping through a bunch of things, but since you asked, this is sort of what our coverage is right now. We're continuing to extend it. We're going to, this part is difficult to fill in. The part that I'm going to put my cursor here, this part is difficult to fill in because guess what? The center of Andromeda is there. The bulge is there. Things are just too crowded. We can't do spectroscopy there, but we are going to extend the coverage a little more to the lower right, to the extreme southwest. There's another hole in this map, and that's this thing that I'm putting my cursor on. That's the center of M32. Again, things are very crowded there. But one of the things we're really, really interested in is looking at tidal debris from M32 and looking at the kinematics of that compared to stars in the disk. How is M32 affecting the Milky Way disk? Sorry, the M31 disk and vice versa. The reason the colors change around M32 because M32 has a very different velocity, line of sight velocity, than the local disk of Andromeda. Right? M32's colors are more like -200, whereas this part of Andromeda's disk is more like -400. So that's convenient because there's we don't know whether M32 is in front or behind, but we have a good velocity separation. This is Doug Grion-Filio's PhD thesis. M33 is different from M31. If you look at its age versus velocity dispersion, it's fallen down and it can't get up. It's all flat, all ages, all types of stars, low dispersion. So whatever's happened to M31's disk certainly hasn't happened to M33. So it's not and M30 and the Milky Way disk appears to be somewhere in between. This is a very busy plot. I just want you to focus on these three stars over here. These are young, intermediate age, and old stars in M33's disk. All have low dispersion. Now, mind you, M33 disk is a little more face-on than Andromeda's disk, so we're closer to, our line of sight is closer to looking at the Z component, but there's really no significant difference, no significant trend with stellar age. We are seeing some dynamically hot stars in M33, but they seem to be concentrated near the center of the galaxy. Trying to make sense of this. They're seen in old stars, they're seen in intermediate age stars, they're not seen in young stars. Young stars are purely cold. This is what I mean by two component. We don't see anything like that in M31. In M33, clearly, there's a cold and a hot component that you can fit to. Okay, this is the work of Lara, Amanda, and Carrie. This intermediate age work. Intermediate age stars show a slight hint of a dynamically hot population, as shown by that fit there. The percentage is lower than for old stars. And this is the work of Lara Cullinan, Johns Hopkins postdoc. All right, I think I'm not going to talk about beyond the local group. I'm going to go straight to my summary slides. Am I?
You have 5 minutes.
5, okay. I'll take a couple of those minutes to talk about a certain mystery we're trying to uncover. The three spectra you see here are stars in the disk of M31. And these are carbon stars. So these are stars whose absorption is completely dominated by molecules like C2 and CN. In particular, there's a very strong feature at 8,000 angstroms that's shaped like a W, and that's produced by CN. You can see that in the highlighted band there at 8,000 angstroms. We started to see these stars that don't look like this. Normal stars have calcium triplet, titanium oxide. They have a more smooth continuum. But we started to see these stars. You can see the calcium triplet highlighted in the blue band. You can see titanium oxide at 7,100 highlighted in the blue band on the left. But if you look in that pink band at 8,000 angstrom, you see a hint of that W. It's a faint version of the CN feature. So we're calling these weak CN stars. Now, I have no idea what to make of them, except that based on where they land in the color magnitude diagram, we can tell that these are massive stars, 5 to 10 solar mass stars, that have evolved off the main sequence. They're in the helium burning phase. They're in the, they're in the, they're what are called core helium burning stars. They're interesting in that they show oxygen-rich features and carbon-rich features. So when I was studying spectroscopy on my mother's knee, I was taught that there are stars that are oxygen-rich, stars that are carbon-rich. These things seem to fall somewhere in between. We've tried to look at these stars in an objective way. We've created templates, carbon star templates, and templates for these stars, and we've come up with an automated way of classifying these things. They look like they're the tail of some distribution of normal stars. The carbon stars are completely disjoint, but these are, they form sort of a tail in that space. This is the work that Katie Hamren started with carbon stars, and it's being continued by a team of students. And finally, Doug is writing this up. Doug and I are writing this up now. All right. I think these are the things I've talked about today: accretion history of the Milky Way through the lens of Halo 7D. I didn't get a chance to talk about BP3M, but I talked about NGVS. But there's a paper on the archive, BP3M, that Kevin has published, and talked about M31 stellar dynamics. I didn't get to talk about detailed forensic reconstruction of one of its satellite interactions. That was through the lens of SPLASH and a few HST surveys. And finally, talked about M33's disk a little bit. And I think I'll stop here. Thank you.
Questions for Raja? Yes, Zach.
For the Milky Way stellar halo, how were the main sequence turnoff stars that you found selected?
They were selected based on a couple of things. We have Hubble images, so they're point-like image morphology. We selected boxes in the CMD that are the appropriate color for them to be main sequence turnoff stars. We didn't go too far to the red with the selection. We gave lower priority to things that are too blue to be main sequence turnoff stars. Some of those turn out to be quasars. They turn out to be helpful in an indirect way. The quasars that we find, when we measure their proper motion using, the same, if you assume they're a star, we use the background galaxies as the reference frame and measure their proper motion. What is beautiful about these quasars is they have a proper motion of 0. And the few quasars that we found spectroscopically, they all have proper motions consistent with 0. That let us, the size of that quasar cloud is completely consistent with our estimated proper motion errors. So that tells us that we're measuring errors properly and that we are things that spectroscopically identified as background objects are turn out to have 0 proper motion. But it's essentially CMD selection, image morphology based, and then the main contaminants are quasars.
So when you did the spectroscopic search, did you turn up any spectroscopic binaries or anything in there within that mix, or?
We don't know because the spectroscopy was difficult enough that we have a single epoch. And it would be interesting to go back and re-measure them. But we don't know at this point based on the data.
Regarding the CN that you just talked about, my recollection was, I just checked that Alpha Orionis, which of course is an oxygen-rich supergiant, has CN bands.
Wow.
And I was just found the paper.
Please send it to me.
Okay, I mean, I just Googled it.
And it said, so Alpha Orionis.
Betelgeuse.
And, Betelgeuse. Okay, and what is its mass?
And solar mass.
10 solar masses. Okay, that's
So, compared
5 to 10 is what we are seeing here. And it has carbon bands.
Yes, I mean, they're not, I don't know whether there's the ones that you see and whether they're as strong as those, but it definitely is.
No, our challenge has been to find analogs in the Milky Way, right? Because massive stars in the optical in the Milky Way are difficult to reach because they're in the disk and they're mostly obscured. They're in open clusters that are mostly obscured. So it's no surprise that this is a nearby very nearby star. And I'd love to look at that. And you said that there's hints of carbon bands in there.
Yeah, there's a paper on the C12, C13 ratio based on CN.
Wow.
So,
Okay, that's great. That's great.
but my other question had more to do with your main topic, which you were talking about the Andromeda being hotter, and you invoke possibly the bar as one of the stimulators. What are the other possibilities, and how does the bar in Andromeda compare with the bar in the Milky Way?
I haven't kept up with the bar in the Milky Way, to be honest. The bar in Andromeda was found in beautiful near-infrared imaging. I don't remember which survey was that. It predated Spitzer. I think it was from the TUMAS data that this was visible. Especially visible in so it was J, H, and K imaging in Andromeda. And if you fit ellipses to the bulge region, what you get as residuals is beautiful Maltese cross. Basically the corner, it's a box-shaped bulge. You can see that very clearly in the K band. In the J band, there's enough dust lanes and so on that it's not as clear. The extent of that is a few kiloparsecs, I guess 1-ish kiloparsec or 1 to 2. And at the end of that, you do see some extra dispersion. So we think the bar is doing something. The Milky Way, we don't have comparable measurements, right? Because the Milky Way samples are solar neighborhood samples. So I don't have a direct answer to that. I don't know how to do that comparison. Clara has her hand up in the chat.
Yeah, go ahead, Claire.
Yeah, very nice talk, Raja, with so many interest topic. So my question is about the Aralaires NGVS dataset. So if I understood correctly, you said that the most distant Aralaire was at 450 kiloparsecs. So how confident are you about this kind of Aralaire? Did you do some follow-up to confirm like did you check like the light curve is good, or like how about the completeness at this distance?
Yeah, so the most distant one is not that distant. It's 300.
Okay.
Not 450. And we've injected a lot of fake RLRA. We've taken bright RLRA, added noise, maintained, realistic cadence, realistic photometric errors, and we've injected them into the algorithm. And very, as expected, the density profile I showed you and the stars I showed you, those are all RRABs, they're not RRCs.
Okay.
And the completeness falls off a little faster for RRCs because the amplitudes are smaller, and more symmetric light curve, a little more easily confused with other things. So the RRC falls off about a magnitude brighter than RRAB, but for RRAB, at 300 kpc, we're still, I think the completeness is something like 80%. So the paper has the details of the completeness as a function of magnitude from these from the RLRA we've injected. We have spectra, but not out to 300 kpc. It's just the stars are too faint. We have spectra between about 80 and getting up to close to 200 kpc. Over that range, we have spectra of many objects. Most of them have turned out to be RLRA, a few have turned out to be background quasars. The other way we find background quasars, this is sort of an indirect way. Let's say it's a suspected RLRA with or candidate RLRA where we have a period, we have phase, and we know when we're going to measure a spectrum. We know how bright it's expected to be. We go to the telescope, we take a spectrum, the conditions are absolutely fine, but we don't see any continuum. This thing has faded compared to what it was supposed to be. And there's a few cases like that, a handful, 3 or 4 cases out of the close to 100 now spectra that we have. And those we think are also quasars that they have some long period variation that we are picking up indirectly through our spectroscopy.
Thank you, Raja. So another question I have, if I may ask another one. It's about so have you checked in the whole like data set of Aralides if you have some clamps stars like at such a long distance that could indicate like there is a new like ultra-faint system around that hasn't been detected because you reach very deep, and I don't know if other surveys have been able to reach that deep in terms of Aralides.
We don't see any evidence of substructure beyond the Sagittarius stream, but our numbers are very small. You know, we have close to 200 stars, half of them part of Sagittarius, and for the remaining, 100 or so stars, it's difficult enough. It looks consistent with a smooth power law, but that's not to rule out that there's substructure. There's, as you said, there's certainly substructure there. We don't have dense enough sampling to tell.
Okay, thank you.
Thanks.
Okay, I think we're running close to time. Raja, I noticed you brought some crest flyers. I wanted to respect that if that was something that you wanted to share with the audience.
Happy to do that. Happy to do that. So I'll just take a minute to talk about this. CREST stands for Creating Equity in STEAM. This is an initiative that is not unlike others at other campuses. We started this a month after George Floyd's murder. We started this on 25th of June, 2020. And the idea is to, through a variety of programs, engage young people, especially young people around the world and educators around the world, and literally anyone who's interested in the science that goes on. Now, and I don't mean the science of astronomy only. We started with astronomy, but in all of these cases, we are quickly spreading beyond astronomy. So there's a program called Shadow the Scientist that Brian and Roy Gal at IFA have been hugely influential in setting that up on Mauna Kea telescopes, on Gemini, Subaru, Keck. We've now expanded Shadow the Scientist to biology, and we're about to expand to fieldwork in ecology. And it's a very simple concept. When someone is doing their research, very often the equipment they use is being controlled by a computer. But that computer can be shared, the screen can be shared, and by Zoom, students can see what scientists do for their work. That's how we connected to Sunny and Azrael in the first place, through Shadow the Scientist, and then they've come on to do a deeper dive with, we teach an online class that's Python in the context of research, and then an even deeper dive is coming to campus for the summer and working with a PhD student all summer on a piece of a research project. So that's what CREST is. It's an umbrella for this range of programs. I have some brochures if you're interested, please. And this is one of these things that really doesn't have institutional boundaries. We're trying to break these institutional boundaries. If you're interested in being a host for a shadow session, doesn't matter which institution you're with. I mean, our hosts so far have been from a variety of academic and non-academic institutions. So. All right, thank you.
And I want to shout out to Zach Hartman too for doing our first Gemini North Shadow the Scientist, hosting our first Gemini North Shadow the Scientist. And we're going to be doing 2 sessions coming up on December 9th and December 11th, both of which Zach's going to host. So we're starting up again.
And that's in Q mode, which is,
yep.
You guys are the first observatory that's shadowing in Q mode. All the others have been classical mode.
Okay, I think we'll leave it there. So let's thank Raja again. And Raja will be around for the next couple hours in case anybody wants to meet with them. Office 129.